Alright, guys, and welcome to Universe Sandbox 2. Today, just wanted to quickly talk about Kepler 90 again. There's some stuff that I forgot to mention in my last video, so let me just start a new simulation quickly. Now, what I forgot to mention in my last video about Kepler 90 and that new planet that NASA discovered within it is the way they discovered it. Now NASA, as far as I understand, has now there's one gentleman, I forgot his name right now, but Anton Petrov actually talked about him as well on his channel. What the Math? Yes, that's his channel name. What the Math? I actually recommend you going to Anton Petrov and his What the Math channel, where he talks about this kind with this as well. Anyway, this gentleman, he developed this program, this algorithm that has been programmed to help them search for planets, and using current data from the Kepler spacecraft. Now, this algorithm, if I remember correctly and understand it correctly, this kind of high programming, computer programming, is not exactly my strong point. Yeah, I'm not a computer programmer, so it's beyond my skill sets, but it has been programmed to look for certain parameters in the Kepler spacecraft, and this is how they discovered that eighth planet. Of course, they checked if the information that this algorithm gave them is correct. So they checked. And then rechecked it, and when they were sure that all the evidence was correct, that's when they announced it. Once they've confirmed that the algorithm was giving them the correct information. But I suggest you guys check it out for yourselves by Anton Petrov as well. He will be able to explain it much better than what I can right now. But let me just show you the two of the methods that astronomers use in discovering planets. Okay, so that's our star, and here's our first planet. Yeah. Now, okay, good. Now, that was fast, but yeah, when a planet passes in front of a star. Okay, let me just quickly slow down time here a bit because it's gonna go way too fast. Just want to show you guys. Okay, now, okay, but well, I must unpause it first. Yeah, when a planet passes in front of a star like this, then it blocks some of the light coming from its host star, and this is what this algorithm is looking for. It can do it far better than what any person can. It's far more accurate than what a person can do. Now, depending on the size of the planet and the distance of it from the star, it blocks more or less light. But like I said, it depends on the size and distance of the planet from its star. Now, up close like this, you can actually see the planet itself blocking it. But if you're really far like this, then you can't really see it. But sensitive instruments can detect it, like what the Kepler spacecraft does. It looks for these transits. This method is called the transit method, and this algorithm looks for any transits that the Kepler spacecraft may have missed. And with the Kepler 90 system that I talked about just the other day, the algorithm found a planet that the Kepler spacecraft actually missed. It's not perfect, but it's the best that we have. I know a lot of people will say, "Oh, but the spacecraft made a mistake. Space doesn't exist." Ugh. Yeah, I know we're not. NASA isn't perfect. The instruments that we have aren't perfect. Yes, but it's the best that we have. And stop blaming us. Stop blaming NASA for being the way they are. We're people. We make mistakes and we learn from these kinds of mistakes. Anyway, to method number 2, the radial velocity method. No, not that one. Let me just pick this one. Jupiter. Now with the radial velocity method, you will see now what that method is. Let me just speed up time a bit more. And you will see now what's going on here with this method. Just let Jupiter go around the star a bit, and there you see it, guys, over here, that line, that's the star's path. Okay, in reality that doesn't exist, but here in Universe Sandbox 2 you can actually set it up so that you can see the paths of these planets and stars. Now, all planets, let me just pause it quickly. Now, every planet pulls on their host stars. Now, how much they pull on the star depends on how massive the planet is. Now, small rocky planets like this one, for example, they don't pull on their host stars that much. Now, every object that's orbiting a star is orbiting around the barycenter of the system. Now the barycenter is basically just a moment. Let me think quickly. It's basically the let me show you guys quickly with a new one. Now it's basically the no, not that one. That one's too big. The gravitational center. This will actually show you guys better what this is. Now, as you can see, these two stars are orbiting around their barycenter, and I just got it, their common center of mass, which would be roughly over here, roughly. Now, this this is basically the point around which a star and a planet orbit each other, the center of mass, and depending on the mass of the planet, whether it's a small rocky planet or large Jupiter-sized planet, the center of mass moves accordingly. Now, a small rocky planet, like the Earth, for example, would pull on a star only very slightly, so the center of mass or the barycenter or center of mass between the Earth and the Sun is actually near the center of the Sun, actually, because the Earth pulls on the Sun only very slightly. But Jupiter, actually, with the Jupiter and Sun barycenter, the barycenter is very close to the surface of the Sun, and that's where Jupiter and the Sun orbit each other around that barycenter or center of mass. But let me just quickly start a new system. No, too big, and way too big. Yeah. Now let me just start with this again quickly. No, with this. And let me just speed up time. Now with the center of mass, with this, what's going on with the, now as the planet, now like I said before, depending on the mass of the orbiting planet, the barycenter may either be just at the surface of the star or near the center. It depends on the mass of the planet. Now, as you can see here as well, the star gets pulled first to one side and then to the other side. No, man, go away. Now, as the star gets pulled to either side, so its light curve also changes. Now, astronomers use this Doppler effect to view a star's incoming light. Now, let me give you an example of the Doppler effect. If you've ever heard of a siren, if you ever heard a police or ambulance siren, then you heard of the Doppler effect. Now, as the siren moves towards you, it gets louder, but then as it moves away, it gets softer. Now, sound is made of sound waves, and as the siren moves towards you, the sound waves get shorter, no? But then as the siren moves away, the sound waves get longer. The same goes with light. Light also moves in the form of waves, no? And when a star moves towards or away from us, so the light waves also get longer or shorter. If the light waves moves towards us, they get as the light waves move towards us, they get shorter. But when the star moves away from us, the light gets longer. I actually have a thing here that I can show you. This is the a spectrum from okay, it's actually from a galaxy, but it actually in a way demonstrates what I'm talking about. With the spectrum here, it can it actually shows what I'm trying to tell. Now, a star's light is basically the same as this. It can be viewed similarly as this. When a star moves towards us, the light waves get shorter, so they get bluer. No, this would light that's being squeezed together, that's moving, light that's man, sorry about that. If a star is moving towards us, the light waves get shorter, so they move towards this side of the spectrum, towards the short end of the spectrum. But if the star gets pulled away from us, the light waves get longer, so they move towards the red side of the spectrum. They get red shifted. Towards us, they get blue shifted. Away from us, red shifted. And yeah, I hope I haven't forgotten anything. But this is just what I wanted to talk about, guys. About two methods that astronomers use to discover new planets. The radial velocity method, or Doppler radial velocity method or Doppler method, and then the transit method. Now, both these two methods are quite useful in discovering new planets, and red dwarf and brown dwarfs, but that will be in a new video. But I just wanted to talk about these two methods. So there are several other methods, but I'm not gonna go into them today. Maybe in a later video. But that's about it for now, and I hope you guys have a wonderful day or evening or wherever or whatever you guys are doing right now. Okay, let me just end this video with a bang. Okay, so let me just go to tunes and explode and type 1A supernova and 2 and then we're gonna end this video with a bang, and there they go, and the Earth is gone, but Jupiter is still there, and it's wow. Let me just pause this quickly, yeah, and it has a temperature of 127,645 degrees Celsius. That's really hot. It's really hot. And we just created a nova remnant with a supernova remnant. In my next video I will be talking about I will continue with my planet series and how they formed. Yeah, I will talk more about planets and their formations, how they formed, and yeah, that will be it for this video, and I will see you in my next video. Have a good one.